Today we're going to be looking at Susan Album Party, which is an easy forensics challenge from San Diego CTF 2022. This challenge is fairly straightforward in its presentation, but there is a slight complication that might catch newcomers off guard. The prompt reads, "My friend Susan is having a photo album party, but she accidentally corrupted the SD card with all her photos on it. Can you save Susan's party by recovering her photos?" To go along with this challenge, we are given a single file called stub. Now on my computer, when I pull up this file in my file browser, it actually has a thumbnail. On your system, this might not happen, but I bet if you give it the extension .jpeg, it probably will. I can even double-click it, and sure enough, it's just a low-res picture of a note, handwritten with a 0.7 Pentel Graph Gear 1000. Once I've decrypted the horrific handwriting, I'm still left with what resembles only the beginnings of a flag. We are clearly missing some more pictures. The prompt did say that there were multiple photos on this SD card, so I think what we're looking at is the first JPEG on the card, but there may be more in the file after this one. Now, if we were experienced at forensics, there are probably some tools in the basic forensic toolkit that we would be immediately using in this situation. We will get to those, but first let's just pretend we have no idea where to start. If you just Google how to recover images from an SD card on Linux, you're mostly going to find recommendations for TestDisk/PhotoRec, which is essentially a tool designed specifically for deleted file recovery. It is a bit much for this situation, since we're only talking about a small file instead of an entire disk, but on Linux, you could probably create a loopback device for the stub file and then run PhotoRec on that, and in general, this will actually work. But you probably don't want to do it this way. It's a little bit more heavy-handed than it needs to be for a simple case like this. The other reason I'm not going to show this method fully is because for this very specific challenge, it actually will not work at all. We'll talk about why in a minute. For now, let's just try some simpler tools. If you're using Kali, you should have access to a command line program called Foremost. This tool is specifically designed to extract files from another file using common file signatures. They even show an example of pretty much exactly what we're looking for. Let's run it. I'm giving it the -v flag for verbose output, telling it I want to extract JPEGs, and I want it to target the stub file we have. Spoiler alert, it also doesn't find anything. And this seems odd since we know for a fact that there's at least one JPEG in this file. I will tell you why it couldn't find anything in a moment. Let's get back to this. Let's try one more tool first. Binwalk is another forensics program that is technically designed to extract files from captured firmware, but it works in essentially the same way by just looking for common file signatures and extracting them, so it should work. We can run Binwalk on the stub, but all we get is the familiar stench of nothing. We know that there's a JPEG in this file. Maybe we're just not using these tools right. Let's try running Binwalk on my wallpaper, which is a PNG. Of course, this doesn't work either. It works fine. Well, maybe Binwalk just doesn't have a signature for JPEG files. The only problem with this idea is that we can pretty quickly disprove this. Binwalk is open source, and we can take a look at its signature file for images. Here's the section for PNG, and this is the whole thing. Now, we can scroll down just a little bit and find the section for JPEG images. Okay, you know what? It's still going. Wow, okay. There's quite a lot here. Geez, okay. I guess JPEG images are non-trivial to parse. And as it turns out, that right there is the crux of the issue. The reason why PhotoRec can't find the images in this file, the reason why Foremost can't find the images, the reason why Binwalk can't find the images, it's all because of one simple fact. JPEGs are cursed. I'm actually being serious. If you don't believe me, read some of the comments on the JPEG signature here. It would be great if we could do pointer arithmetic like in an assembler language. If only there was some sort of looping construct or named accumulators. That's right, you need a full-blown Turing machine to properly parse JPEG files. If you still don't believe me, go read the original specification. It's only 186 pages, so I'm sure it can't be that complicated, right? All right, The point I'm trying to make here is that unlike a lot of other file types, forensics tools are not the best at detecting JPEGs specifically. The signatures in these tools, by necessity, need to be a little bit picky about what kinds of JPEG they will recognize, since they would otherwise suffer from frequent false positives. If you know you're looking for one, you may need to get your hands dirty and go about the process a little more manually. We can read a much terser summary of JPEG structure on every student's best friend, Wikipedia. In the syntax and structure section, we can see that the beginning of a JPEG file is marked with the bytes FFD8, which is also the first part of the flag that we saw in the thumbnail, so let's try using this byte sequence. We can actually get binwalk to tell us where these byte sequences occur in our stub file. It looks like there might be 3 different JPEGs in this stub, and now we just need to go about extracting them. In the write-ups for this challenge, I saw a lot of folks using CyberChef to solve this one, which, quite frankly, is just a little bit jank, but I could show that real fast. With the 3 offsets we got from binwalk, we can use the operation drop bytes to trim off everything before each JPEG signature, and what we're left with should be a renderable image. There are also a bunch of different ways to do this from the command line in normal stock Linux as well. For example, did you know you can ask tail to produce a file containing everything after the 30,273rd character? This will output the same renderable image. You can also ask disk destroyer, DD, to make a copy of the original stub file while skipping the first 30,272 bytes, and this will work as well. You can even use XXD to dump the file to plain hex, skip the first 30,272 bytes, and then pump it back into XXD to reconstruct the isolated image. If none of these tools are available to you, you can even write an extremely bare-bones Python script to do it. You don't even need to import anything. Just read the bytes from the original stub file, split the file along its signature bytes, and write a new file containing each section. Oh, but don't forget to write those original magic bytes back first. And that's it. Once we take a look at these 3 images, it becomes clear that these are the 3 pieces of the flag that we were looking for. After combining these, we can submit the flag.